All right, now we want to find a series representation for pi using the fact that arctan of 1 is equal to pi over 4. And then we want to use this series to approximate pi within 10 to the negative 2. So 3.14, right? That's what we're trying to get to. But let's see if that actually works. Well, how are we going to do this? If we know that arctan of 1 is equal to pi over 4, well, we want to find out about pi, right? So that would mean that pi is equal to 4 times arctan of 1. But we have a power series for arctan, right? So this would mean pi would be equal to 4 times the power series for arctan. Now remember what that is? That is negative 1 to the k over 2k plus 1 times x to the 2k plus 1. But in this case, we want to plug in 1 for x. And that's going to be nice enough to go away for us. So this would mean that pi is equal to 4 times the sum. Oh, we should put in the bounds here. So k goes from 0 to infinity. So then pi is equal to 4 times the sum k goes from 0 to infinity of negative 1 to the k over 2k plus 1. And we can bring the 4 inside. So we get a power series, or to get a series, it's not a power series anymore, there's no x. To get a series representation for pi, we would get pi equals the sum, k goes from 0 to infinity, of 4 times negative 1 to the k over 2k plus 1. So that's great. And then we want to know, can we actually find a number from this? Obviously, the more terms we put in, the closer and closer we're going to get to pi. But what do we know about it? We do know that, notice that this is again an alternating series because it's negative 1 to the k. 4 is always positive. 2k plus 1 is always positive. If we can show that it's not increasing and going to 0, we have that theorem about the remainder again. So, non-increasing, so we say that a sub k plus 1 is always less than or equal to a sub k. Well, we would have 4. Maybe we should write down what a sub k even is first. So a sub k is going to be 4 over 2k plus 1. So a sub k plus 1 is going to be 4 over 2 times k plus 1 less than or equal to 4 over 2k plus 1. So notice putting the k plus 1 over here in the bottom made the whole bottom bigger, which made the thing smaller. So yes, we believe that. And if we take the limit as k goes to infinity of the a sub k's, we can see that that goes to 0. So we're allowed to use our information about our remainders for alternating series. So we know that the absolute value of the remainder for the kth term is less than or equal to the absolute value of a sub k plus 1, which was equal to 4 over 2k plus 1 plus 1. And now we want to figure out what that means for n. There's no weird factorials or anything here. All we want to do is make this number be less than 10 to the negative 2. So let's see what that means for k. So 2k plus 1, that's going to be a positive number, right? So let's move it to the other side. 4 less than 10 to the negative 2 times 2k plus 2 plus 1. 10 to the negative 2, that's the same as dividing by 100, so moving it to the other side, that'd be 4 times 10 to the positive 2, or 100, being less than 2k plus 3. So 400 less than 2k plus 3, 397 less than 2k, or we need k to be bigger than 397 over 2, which, dividing that out, that is 198.5. So if k is 199, we'll make sure that our error is small enough. So we would have to add up the first, essentially 200 terms to get within 10 to the negative 2, to get 3.14. All right, now it's asking us to compute the sum of this series. We want to recognize this as some function with some value plugged in for x. Well, notice we have a 2 to the k minus 1, so maybe let's think that 2 is plugged in for x. So let's consider the series k goes from 1 to infinity, k over k plus 1 factorial x to the k minus 1. And remember, that would mean we would care about that with x equals 2. Okay, so now we have a series, a power series, and if we can figure out what function it is, then we could plug 2 into that function and find the sum of the series that we want. So what do we know about this? Well, notice that it has the form something, in this case 1 over k plus 1 factorial times k x to the k minus 1. This kx to the k minus 1 should look like something to you. It should look like the derivative of x to the k. So instead of looking for this series, let's look for the series k goes from 1 to infinity of 1 over k plus 1 factorial x to the k plus some other constant, because we don't know what the constant is. And that's what we get when we find the integral of the series we had before. Then notice that if we multiply that through by x, so x times the integral of, let's call the series we want to find f of x. X times the integral of f of x. So that's going to give us x times what we had before. The sum k goes from 1 to infinity, 1 over k plus 1 factorial x to the k plus c. And why am I doing this multiplying by x? Because I want to make the power of x here k plus 1, so it matches the thing in the factorial. So this becomes the sum k goes from 1 to infinity of x to the k plus 1 over k plus 1 factorial plus c times x. With an index shift, we get the sum k goes from 2 to infinity of x to the k over k factorial plus cx. But now we recognize this. We know, off here to the side, we know e to the x is the sum k goes from 0 to infinity of x to the k over k factorial. So we can rewrite this as the sum k goes from 0 to infinity x to the k over k factorial. What have we added in that we've added in the first two terms? So minus, the first term there is 1, and minus the second term is x to the 1 over 1 factorial. So that'd be x plus dx. Now we can replace this series with e to the x. So this is e to the x minus 1 minus x plus cx. And remember, that was equal to x times the integral of the function we're trying to find. So if we're trying to find f of x, let's divide both sides by x. So the integral of f of x is going to be e to the x minus 1 over x minus 1 plus c. And then taking the derivative of both sides, we're going to get that f of x was e to the x minus 1 over x's derivative. And then both 1 and c are constants, so they go away. And so what we get when we take the derivative is the derivative of the top, which is e to the x, times the bottom minus the top, times the derivative of the bottom, all over the bottom squared. So simplifying, we get x e to the x minus e to the x plus 1 over x squared. And note here that this obviously doesn't make any sense when x is 0. But what we really cared about, remember what we wanted in the first place was when x was 2. So f of 2 is 2e squared minus e squared plus 1 over 4. So whatever number that is, that's the number that we're looking for. All right, now we'd like to identify the function represented by the power series. And here the power series is the series from k goes from 0 to infinity of x plus 3 to the k over k factorial. Well, this looks like a series that we know. We know that e to the x is the sum k goes from 0 to infinity of x to the k over k factorial. So we'd like to just make a substitution, u equals x plus 3. And the question is, are we allowed to do that? Well, we can do that if x plus 3 is in the interval of convergence. But the interval of convergence here is negative infinity to infinity. So yeah, that'll work. So what does that mean? That means that if, we replace this with u, we would get e to the u, so we get e to the x plus 3. Let's do one more of these. Identify the function represented by the power series. Now we have 3k x to the 3k. And here we want to recognize that by having this k out front, it should make us think about derivatives. So what was the derivative of x to the 3k? That'd be 3k x to the 3k minus 1. Since k is a constant here. And that's kind of what we have. We have a 3k x to the 3k. So we have actually x times that, right? So we have x times the derivative of x to the 3k equals 3k x to the 3k. All right, good. So then what does that tell us? That tells us if we look first at the sum x to the 3k, k goes from 0 to infinity. We know what that is. That's a geometric series with x cubed being the r. This is 1 over 1 minus x cubed. Now, to get our series, we want to first differentiate this. So let's differentiate both sides. We would get the sum k goes from 0 to infinity of 3k x to the 3k minus 1. And that's going to equal 3x squared over 1 minus x cubed to the second power. And then we want to multiply both sides by x. So we get x on this side, gives us the series we're trying to find, 3k x to the 3k. And x on this side gives us 3x cubed over 1 minus x cubed squared. And that is the function that is represented by this power series. Now, of course, we have to worry about interval of convergence. So remember, this works if the thing we're substituting in is within the interval of convergence. So the interval of convergence for a geometric series, remember, is r less than or equal absolute value of r strictly less than 1. So we said this was a geometric series with r equaling x cubed. And so we have x cubed, absolute value less than 1, which means x is an absolute value less than 1.